Proposition 47. In right-angled triangles, the square on the side subtending the right angle is equal to the sum of the squares on the sides containing the right angle. Let ABC be a right-angled triangle, having the angle BAC a right angle. I say that the square on BC is equal to the sum of the squares on BA and AC. For let the square BDEC have been described on BC and the squares GB and HC on AB and AC respectively, according to proposition 1.46. And let AL have been drawn through point A parallel to either of BD or CE, according to proposition 1.31. And let AD and FC have been joined. And since angles BAC and BAG are each right angles, then two straight lines AC and AG not lying on the same side make the adjacent angles with some straight line BA at the point A on it, whose sum is equal to two right angles. Thus, CA is straight on to AG from proposition 1.14. So for the same reasons, BA is also straight on to AH. And since angle DBC is equal to FBA, for they are both right angles, let ABC have been added to both. Thus the whole angle DBA is equal to the whole angle FBC. And since DB is equal to BC and FB to BA, the two straight lines DBBA are equal to the two straight lines CBBF respectively. And angle DBA is equal to angle FBC. Thus, the base AD is equal to the base FC and the triangle ABD is equal to the triangle FBC from proposition 1.4. And parallelogram BL is double the area of triangle ABD, for they have the same base BD and are between the same parallels BD and AL from proposition 1.41. And square GB is double the area of triangle FBC, for again they have the same base FB and are between the same parallels FB and GC from proposition 1.41. And the doubles of equal things are equal to one another. Thus, the parallelogram BL is also equal to the square GB. So similarly, AE and BK being joined, the parallelogram CL can be shown to be equal to the square HC. Thus, the whole square BDEC is equal to the sum of the two squares GB and HC. And the square BDEC is described on BC and the squares GB and HC on BA and AC respectively. Thus, the square on the side BC is equal to the sum of the squares on the sides BA and AC. Thus, in right-angled triangles, the square on the side subtending the right angle is equal to the sum of the squares on the sides surrounding the right angle, which is the very thing it was required to show.